A journey to the edge of the observable universe. Did you know there's a universe that can be observed from Earth? Yes. I will take you on a journey through the observable universe in this video. Stay tuned until the end so you don't miss any interesting parts. Let's dive in. First, let's see what an observable universe is. The observable universe is the region of the universe that can be seen from Earth. It is limited by the distance that light has travelled since the beginning of the universe, approximately 13.8 billion years ago. This region is about 93 billion light years in diameter and includes all matter and energy that can be detected or inferred from our vantage point. Initially, scientists thought there might be around 2 trillion galaxies in the observable universe. However, new data from the New Horizons mission in 2021 suggests that there are only a few hundred billion galaxies. Assuming that the universe is the same in all directions, isotropic, the observable universe appears as a sphere centered on the observer. The distance to the edge of this sphere is roughly the same in every direction. What are the challenges faced by scientists when observing the observable universe? Astronomers who look up at space and observe the observable universe face some big challenges. These challenges can make it tricky to study the universe, even with the most advanced telescopes. One big problem is the tools have limits. Telescopes can only see so far and so much detail. This means there are parts of the universe that we can't observe very well, no matter how hard we try. Some things are too far away or faint for our telescopes to pick up. Another issue is that our observations can be biased. Imagine counting all the animals in a forest, but you can only see during the day. You'd miss all the creatures that came out at night, right? It's the same with observing the universe, things that might be hidden from view because of when or where we're looking. Some cosmic tricks make things even harder. For example, dust clouds in space sometimes block our view of distant stars and galaxies. Or, if something is moving fast, it might blur our telescopes, making it hard to study. Now, let's look at the debate on universe versus observable universe. In both popular and scientific writings about cosmology, the term universe is often used to mean observable universe. This usage makes sense because we can't directly observe anything beyond the observable universe, even though many theories suggest that the entire universe is much larger. There is no evidence that the observable universe is the edge of the whole universe. The cosmological models do not propose that the universe has a physical boundary. Some theories suggest that the universe could be finite, but without an edge, similar to how the two-dimensional surface of a sphere is finite in area, but has no boundary. The galaxies we can see in the observable universe are just a tiny part of all the galaxies. According to cosmic inflation theory, if inflation started about 10 to the minus 37 seconds after the Big Bang, and the size of the universe before inflation was about the speed of light times its age, the universe would now be at least 1.5 times 10 to the 34 light years across. So the entire universe could be at least 3 times 10 to the 23 times bigger in radius than the observable universe. Before moving on, let's subscribe to the channel for more cosmic updates. Now, we're going to discuss the edge of the observable universe. The edge of the observable universe marks the limit of what we can see or detect from Earth. This boundary is shaped by several vital phenomena: the cosmic microwave background, redshift, and the cosmic horizon. These concepts help us understand why our view of the universe is limited and what lies at its furthest reaches. First, the cosmic microwave background is a faint glow of radiation that fills the entire universe. It is the oldest light from the Big Bang. Before this time, the universe was so hot and dense that light couldn't move freely. After reaching a lower temperature, protons and electrons came together. Then, neural hydrogen atoms formed, allowing light to travel through space. This process is called recombination, and the light from this period is the cosmic microwave background. Redshift occurs when light from faraway objects in the universe stretches into longer, redder wavelengths due to the expansion of space as it travels. This effect is similar to the Doppler effect, where the sound of a moving object changes pitch as it moves towards or away from you. When objects move away from us because the universe expands, the light they emit shifts towards the red part of the spectrum. Redshift is crucial for determining the distance of faraway objects. The object is at a greater distance if the redshift is higher, and then the faster it is moving away from us. By measuring the redshift of galaxies, astronomers can map the universe's structure and estimate its size and age. Redshift also helps understand the universe's expansion rate, accelerating due to dark energy. Lastly, the concept of the cosmic horizon defines the ultimate limit of what we can observe. Since the universe began, the cosmic horizon marks the furthest distance from which light has been able to reach us. Beyond this horizon, light from more distant objects has not yet had enough time to reach Earth, rendering these regions unobservable. There are several reasons why we cannot see beyond the cosmic horizon. The speed of light is finite. Because the universe is about 13.8 billion years old, the farthest light we can observe has travelled for 13.8 billion years. Due to the universe's expansion, this distance is now about 46 billion light years in any direction, creating a spherical boundary around us. Moreover, the universe has been expanding since the Big Bang. As this expansion stretches space, distant galaxies move away from us. As these galaxies recede, the light they emit takes longer to reach us, and some may eventually move beyond the observable universe as the expansion accelerates. In the very early universe, a rapid expansion known as cosmic inflation occurred, causing the universe to grow exponentially in a fraction of a second. This inflation means that regions of the universe that were once close together are now far apart, some beyond our observational reach. While we can see a vast array of galaxies and cosmic structures within the observable universe, we know there is much more beyond this horizon that we cannot detect directly. The edge of the observable universe is not a physical boundary, but a limit set by the finite speed of light and the universe. Did you know that cosmological surveys and mapping projects provide valuable insights into the large-scale structure of the observable universe? Cosmological surveys and mapping projects are like giant treasure hunts in the sky. They use potent telescopes and advanced technology to map out the vast expanses of the observable universe. One such project is the Sloan Digital Sky Survey, which has been like a cosmic cartographer. It maps billions of galaxies and quasars across the sky. By measuring the positions and distances of these celestial objects, SDSS has created detailed 3D maps that reveal the cosmic web, the intricate network of filaments and voids that make up the universe's large-scale structure. Another survey is the Cosmic Evolution Survey, which has been peering deep into the universe to study how galaxies have evolved over billions of years. By observing galaxies in different stages of their life cycles, Cosmos has provided valuable insights into the processes driving galactic evolution, such as star formation, mergers, and interactions. These surveys are like cosmic time machines, allowing astronomers to peer back in time and study the universe's history. By comparing the distribution of galaxies at different cosmic epochs, scientists can trace the evolution of cosmic structures and better understand the underlying physics driving the universe's growth and expansion. In addition to these large-scale surveys, there are also smaller-scale projects focused on specific regions of the sky or targeting particular types of cosmic objects. Let's talk about the theories and ideas of the observable universe. Scientists have proposed various ideas to explain what might exist beyond our observational limits, ranging from multiple universes to higher dimensions and the concept of finite but unbounded universe. The multiverse theory suggests that our universe might just be one of many existing universes. These other universes might have different physical laws. The idea of multiple universes stems from several sources. Some interpretations of quantum mechanics, like the many worlds interpretation, suggests that every quantum event spawns multiple outcomes, each in a separate parallel universe. Moreover, string theory, which aims to unite all fundamental forces of nature, also predicts the existence of multiple universes with varying dimensions and physical properties. The multiverse theory is speculative, as we currently lack the means to observe or interact with these other universes. However, it remains a fascinating possibility that expands our understanding of the cosmos. Another intriguing idea is the existence of higher dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. String theory defines fundamental particles as not point-like objects, but relatively tiny vibrating strings. For this theory to work, it requires additional spatial dimensions, up to 10 or 11 in some versions. These extra dimensions are hidden from our perception and can lead to certain limitations. Moreover, brain cosmology suggests that our observable universe might be a three-dimensional brain, floating in a higher dimensional space. Other brains could exist in this higher dimensional space, potentially interacting with our universe in ways that could explain certain cosmological phenomena. Now, let's review some crucial points from today's video. The observable universe refers to the portion of the cosmos we can observe from Earth. This region is about 93 billion light years in diameter. It can be detected using telescopes and other observational tools. Beyond this boundary lies the unobservable universe, parts of which are beyond our ability to detect due to limitations in observation. That's all for today, guys. In the comments section, share your perspective, thoughts, or questions.